Till here? Okay, thank you. Good. All right, welcome back to after the break. So, I actually made a nice example, very small example. Right. So here's a situation. We have a graph G, and we have this tight cut C. It happens to be peripheral. Therefore, it has the property of lemma 5.1. There exists an edge with the property that when you delete either end from the corresponding shore, you still have a connected graph. So here are multiple choices. One choice is UV. Oh, I forgot the mic. Thank you. Good. Thank you. One choice is the edge UV, where U and V are actually the two separation vertices. And if you delete U and V, you get this graph. This is a matchable graph, and in fact in this case there are no edges from the left to the right. It's not even connected, so it's not matching covered. Here, if you choose UV as this edge, UV prime, so instead of UV I'm going to now choose UV prime. Observe that if I delete U and V prime from the corresponding shores, I will still have a connected graph. Is that correct? If I delete U from here, I will have K2. And if I delete V prime from this shore, I will still have K2. Yeah? Those are matchable graphs. The two K2s, they are the corresponding perfect matchings. But the edges that are in the cut, partial of x minus u, these two edges, they are not matchable. This graph is only one perfect matching. Right? So this is an example that shows you that in all situations, G minus U minus V is matchable. Either it is not connected or it has edges that are unmatchable in the edges of the cut. So it is never matching covered. Right? So we will have to deal with such graphs. Yeah. So we will have a lemma that deals with this. But before we go to that lemma, which we will go eventually, hopefully today, let's talk about more basic things, right? So let's talk about barriers in matchable graphs. Right, so we have talked about barriers quite a bit, but we will discuss a few things and we will actually generalize some of the concepts we have discussed earlier, right? Okay, so let me ask you, have we talked about cores with respect to a barrier? Can we talk about the core of a graph with respect to a barrier? But at the time we took a matching covered graph, is that correct? We took a matching covered graph, we took a barrier, and the core was just shrink each odd component to single vertex. But now I want to define core for every matchable graph with respect to a barrier. So let's first talk about that. Core of a matchable graph G with respect to a barrier B. Yeah? And the core should be a bipartite graph. Okay? So let's make a drawing. I'll make an abstract drawing. So here is a barrier in a matchable graph G. Barrier definition is of course the same. Yeah? You can use the definition of SGT. It just means that you get as many odd components as the number of vertices in the barrier because the graph is matchable. However, there may be two things that I have not drawn here. What are those two possibilities that may also happen? Even components and edges in the barrier. Just in general, in a matchable graph, if you take a barrier, these things may happen. It doesn't happen in matching covered. So we still want to define core. So I want you all to think about how you will define core in this more general situation. And the core should be bipartite. Not only should it be bipartite, it should also be a bipartite matchable graph. Yeah, okay, so think about it and I'll come and talk to you. Okay. Yeah. Oh, okay, you already did questions on this. Okay, so assignment 1 already has problems related to this? Yeah? Okay, good. Yeah? Okay, anybody else? Everybody figured it out? Right, so we'll do exactly what you expect. We will throw away the bad things. So we'll throw away all the edges in the barrier and we will throw away all the even components. That's how we'll define core. Okay? So in this example, I'll just make a drawing. I'll keep the barrier as it is. I will delete all edges that have both ends in the barrier. I will delete all the even components. And for every odd component, I will make it a single vertex. And this we will call the core. And we will typically use A, B to denote its color classes, where B is the original barrier and A is the odd components. One vertex corresponding to each odd component. Yeah? H, yeah, this is H, math BBH, yeah. Anyways, H is fine. Yeah. Anyways, you can just use H, it's fine. Yeah. Okay, so that is what we are going to call the core. And observe that the core is matchable. You all agree? The core is always matchable. Maybe this is in the assignment. Yeah? Core is matchable. Yeah? Okay, good. But the core need not be matching covered. Yeah? The core need not be matching covered. Okay? In general, the core need not be matching covered. You can make examples. DIY. Construct examples in which the core is not matching covered. Yeah, not too difficult, especially at this point in the course, should be pretty straightforward. Yeah. However, what is very interesting is that there is always a barrier such that the core is actually matching covered. There is always a barrier such that the core is matching covered. In fact, we'll add more properties. There is always a barrier with the additional property that all odd components are critical, also known as factor critical hypermatchable. So we want two properties. We want the core to be matching covered and we want every odd component to have the property that we get in maximal barriers. Right? And therefore you should expect maximal barriers to come into the picture. This is what we will call a Dulmage-Mendelssohn barrier, also known as DM barrier. Okay? So, what is a DM barrier? It's a barrier B of a matchable graph with the following properties such that one, the core is matching covered. I think Lokezi Murthy used the notation just H of B. So the core of G with respect to B, same thing, is matching covered. And the second property we want is that each odd component of G minus B is critical. Will we have even components? Yeah, maybe there. Yeah, could be there. Each odd component of G minus B is critical. Yeah, this is the term they use instead of factor critical or hypomatchable. Yeah, so I'll use it. So this is what a Dulmage-Mendelssohn barrier is. And these barriers will play an important role in the proof of the ELP theorem that we are going to see. But I think they also play an important role in other places. I'm not sure yet, we'll find out. But this is definitely one place where they play a very crucial role. And here is a lemma that is not too difficult to prove actually. In any maximal barrier of a matchable graph, there is a Dulmage-Mendelssohn barrier. Inside every maximal barrier, you can find a Dulmage-Mendelssohn barrier. Yeah, let me just make sure I'm not getting anything wrong here. Matchable graph. Every maximal barrier of a matchable graph contains a Dulmage-Mendelssohn barrier. Every maximal barrier. Remember, we don't have the canonical partition theorem. This is matchable graphs. Wait. Every maximal barrier V star of a matchable graph G includes, as a subset, includes a Dulmage-Mendelssohn barrier. B could be equal to B star. Furthermore, all the odd components of G minus B are actually odd components of G minus B star. Therefore, they are going to be critical because B star was a maximal barrier. So the critical part will just come from the proof very easily. Furthermore, each odd component of G minus B is an odd component well, I don't need to say odd, it is a component of G minus B star. Maybe we should look at an example, right? But then I will solve the DIY. Okay. Let's make an example. It's not too difficult. Maybe you should all try to make an example. Can you all try to make an example of a barrier such that the core is not matching covered? Make it a maximal barrier if possible. Should not be too difficult. But inside the barrier, there should be a Dulmage-Mendelssohn barrier. Let's see if you can make such an example, and I will come around. Okay, I'll come. Okay, and now we'll be delving into the barrier. Which satisfy these two properties. So this is a maximum value. So in the maximum value, I have to find it. Maybe it is a terminal. Each component is critical that we can see. Actually, this is not the. This is not magic cover. So inside it, I have a value. Only single item. Which one? This one. Not clear. Component is not vertical. Only two choices are here. Okay. Now make non-bipartite example. If you have a bipartite example, make a non-bipartite example. So your graph is this. So what is the level of the value? The nature of the properties. So it is Bernoulli Nelson because the core is actually C4 with multiple edges, and the components are K3. Okay, but can you make it? Okay, now you're saying that you can also make it. Okay, and then is that dimension? Yeah, so can you make a situation where the maximum barrier itself is not Dalmas-Mendelssohn, but there is a Dalmas-Mendelssohn barrier inside it? In a matching graph, yes, a matching graph. Yes, that property will be true, but the other property won't be true, right? The core will be matchable, need not be matching graph. Core need not be matching graph. Core is a bipartite matchable graph. Need not be matching. Okay. Anybody else? No? No? Yeah, so the concrete question is, construct an example in which B star, the maximal barrier, is not Dalmas-Mendelssohn barrier, and locate B. B will be included in B star, but B should be a Dalmas-Mendelssohn barrier. Right, and make a non-bipartite example. But bipartite is where you start, right? So you want to make a non-bipartite example, you start from bipartite, and then you reverse engineer your way. Might be the only place where I use the word engineering. Yeah, I think this age, maybe that way. I'm trying. When you just said that we were engineering not bipartite. paper.
I just came straight.
Okay.
But like, so you consider all the components.
Paper. Okay. Make a drawing. Good. Thank you. Okay.
This value. So I'm basically have these 5 components. These 3 are showing complete width to these 3. All of this is showing it is, and all of this is showing. So there is no edge like this, so it's not matching color. These are critical, but that doesn't matter. So this is maximal barrier, but it's not a DM barrier.
Right.
And for DM barrier would be this.
Okay. Good.
So these 3 will be the components. And this 4 will be the components.
Okay. Now we
This
can
will
talk
be
about
like
it.
this.
Okay. Make it highly non-backward.
This time I made that it is non-bipartite, but it is B star and B are same.
Okay.
So yeah, this is a value, this is and the so these 2 are of components that are critical, and there
The graph is not matching. Code is not matching.
core is going to be this one, no?
No. This edge will be there in the code. Code will have an edge. Right. And code has to be matching code. It cannot be disconnected. Okay, good. Anybody else? Yeah, okay, I'll come to you. So what is a B? B star. Okay, sure. Okay, good. Anybody else? So, anyways, I won't draw the example. You all can figure it out, right? So, yeah, got it? Okay. Okay, so what I want you to try is I want you to try proving this. It's not difficult at all, actually, but we will prove it in the next lecture, anyways. Yeah, this is quite easy. But now I want to state the result that is not as easy, but maybe before that, let me state one more easy result. This is DIY even in Lucchesi Murthy, it's that easy. This is a DIY. If I give you a DM barrier, then every edge of the core is matchable in the original graph. G is a matchable graph. B is a DM barrier. Then the result is that each edge of the core is matchable in the original graph. Notice that the edges of the core, they correspond to edges in the original graph. Right? So that's what this result is saying. It's not too difficult. It's a DIY. Yeah. And now let me state the non-trivial result. This is going to be related to this situation. Yeah. So we have exactly this situation. We have a matchable graph. We have a cut of the graph whose both shores are inducing connected subgraphs. So let me write it like this. X is a non-empty proper subset of the vertex set of the graph such that the graph induced by X and the subgraph induced by X bar are both connected and we have one more assumption, which is that no edge in the cut is matchable in the graph, which is exactly what happened here. The edges of the cut are not matchable in this graph. Of course, this would be an empty set. I never said the graph is connected. No edge of partial x is matchable in G. Then there is a Dulmage-Mendelssohn barrier that is completely contained in one of the shores, and all the odd components are also contained in the same shore. Then we already know there is a Dulmage-Mendelssohn barrier. Take any maximal barrier, it will contain a Dulmage-Mendelssohn barrier by this lemma, which we are yet to prove. But this is saying something stronger. Then the graph G has a Dulmage-Mendelssohn barrier B such that B is completely contained in one of the shores, such that B is a subset of one of the shores of partial x, so either x or x bar, and additionally the vertex sets of all the odd components of G minus B are subsets of the same shore. Right? So this is my x, this is my x bar. Then the barrier itself has to live in this shore or the other shore without loss of generality. Let me put it here. This is supposed to be a Dulmage-Mendelssohn barrier in the graph G, and all the odd components, they should live in the same shore. Yeah? Is the statement clear? Since we are almost at 7 p.m, I'm going to put this also as TIY today. I'll suggest an order for the TIYs because of course you will not do all of them. But hopefully you'll try some at least. What I suggest is try the easiest first. Try 5.2. 5.2 is essentially trivial. That's a DIY. Then try 5.4. Right. So here's the order proposed, suggested order. 5.2. Finish it off. 5.4. Not too difficult. Your assignment 1 should help you. Let's see. 5.1 and 5.5. I would say 5.1 is easier. but it's not related to Dulmich-Mendelssohn barriers, but it is related to the statement of this lemma, so it will also motivate you to finally try 5.5. Yeah. So today is Monday. You have Tuesday, Wednesday and Thursday to try all of this. And yeah, we will prove all of them on Thursday, and then next week we will prove the ELP theorem. Yeah, I don't want to go too fast because the truth is I am also in some sense learning this material. I mean, I have studied these proofs before when I was reading the laminar ELP conjecture theorem proof, but yeah, definitely I've never taught this material before. So yeah, and it's been a few years. Okay, so that's all for today. Any questions, concerns? Are the statements all clear? Yeah?
Explain the statement of 5.5.
Explain the statement? Let's do it. Good. We have two examples here. Let's find Dulmich-Mendelssohn barrier in both of these. Right? Let's do it. So in this graph, we want to find a Dulmich-Mendelssohn barrier. Well, they are very small examples, admittedly. So let's find a Dulmich-Mendelssohn barrier in this graph, such that it is in one shore and all the odd components are also in one shore. That's very easy here, right? Yeah. So do you all agree? This is a Dulmich-Mendelssohn barrier in this disconnected matchable graph. It is on this shore and the odd components are also on the same shore. Yeah. So this B works. Now let's do this example, which is a bit more interesting. Again, I want to find a Dulmich-Mendelssohn barrier which is on one of the two shores, and all the odd components should be in the same shore. I did not try this one. Let's see. If you find it, let me know. I'll come and talk to you. Degree 3, everybody agrees, degree 3. Okay, let's try the degree 3 vertex here. It is a barrier, I get one odd component. The core is just K2. The component is hypomatchable, vector critical, yeah. So it's a Dulmich-Mendelssohn barrier, yeah. And it is on one shore, of course, a single vertex, nothing to be done there. And its only odd component is in the same shore. That's what the statement is saying. Of course, these are very trivial examples. See if you can make more non-trivial examples and check the statement on those examples, right? So we want the Dulmich-Mendelssohn barrier to be on one shore and all the odd components should be in the same shore. Yeah? Yeah? Okay, any other questions, concerns? All good? Okay, so please try them yourself, all of them, and we will continue on Thursday. On Thursday, my goal is to prove all of the results and not actually start the proof of the ELP theorem, most likely. Most likely we'll start that on Monday and hopefully also finish it on Monday. Yeah? Okay, thank you. Have a nice 3 days, I guess, solving the TI-wise.